Have you ever imagined standing next to a star so immense that our entire solar system would vanish inside it, as if it were nothing but a single grain of sand? Tonight, this journey is crafted for you. If you've ever gazed at the night sky, feeling the quiet pull of curiosity, that subtle ache to understand the scale of the universe, you are exactly the audience this experience was designed for. In the next few minutes, your mind will drift across the cosmos to witness stars so vast, so impossibly colossal, that even the brightest sun you know becomes insignificant, dwarfed by giants that consume billions of times more energy. Picture light taking hours to cross the surface of a single star. Imagine the heat, the brilliance, the unstoppable nuclear fires burning inside it, and know that these celestial giants have lived, pulsed, and sometimes already died, long before humans could even begin to record history. Settle back, take a slow breath, and allow yourself to float as we enter a universe where scale and time stretch beyond comprehension. If you feel a spark of wonder, a shiver of curiosity, or a quiet thrill, consider gently liking this video so others seeking the same calm, awe, and sense of discovery can find it. Tonight our sun, warm and vital as it is, becomes only a whisper in the presence of red supergiants and blue hypergiants, whose diameters exceed 2,000 times that of our sun, whose fusion furnaces burn through hydrogen at rates that would obliterate our imagination, and whose lifespans are fleeting blinks compared to our own star's 10 billion year story. Why does this matter to you? Because these stars, in their enormity and their fragility, reflect the beauty and impermanence of existence itself, reminding us of the cosmic forces that shape everything around us and even inside us. Over the next chapters, we will explore stars already in the twilight of their lives, their outer layers swelling and pulsating like living organisms, shedding vast clouds of gas that will seed new stars and planets for generations to come. We will glimpse blue giants burning furiously, a few million years old, yet shining millions of times brighter than our sun, and we will consider the first-generation giants of the early universe, hypothetical quasi-stars and dark stars, whose size and energy would make even today's largest hypergiants seem modest. By the time this journey unfolds, you will understand not just why these stars dwarf our imagination, but also feel the quiet thrill of witnessing cosmic extremes while lying in your own bed, letting the universe lull you towards sleep. Allow your thoughts to expand, your heartbeat to slow, and your mind to float across distances measured in thousands of light years, because tonight the universe is not distant. It is near, intimate, and yours to explore. Share this voyage gently with someone who craves wonder, who longs for calm, and who needs the universe to remind them how small we are, yet how alive imagination can make us feel. You might think you understand size when you look up at the night sky, but the truth is that what your eyes see is only a whisper of reality. Tonight, you're about to meet stars that make our sun seem laughably small, these stars so enormous that planets like Jupiter and Saturn would vanish inside them without leaving a trace. Imagine, if you will, a single blue supergiant, its surface temperature exceeding 20,000 degrees Fahrenheit, burning millions of times brighter than the sun, yet only a tiny point of light from Earth, hiding in plain sight across hundreds of light years. These are not distant myths or abstract concepts. They are real objects governed by the same physics as our sun, yet pushed to the extreme, stars whose gravity, pressure, and fusion reactions challenge the limits of human comprehension. And tonight, you, lying quietly in your bed, will journey alongside them, Consider R13601, a blue hypergiant in the Large Magellanic Cloud, over 2,000 times the radius of our Sun, containing more than 200 solar masses. If placed at the centre of our solar system, its outer layers would extend far beyond Saturn, engulfing Mercury, Venus, Earth, Mars, and the asteroid belt in an instant. The sheer energy it emits every second is so vast that it dwarfs entire galaxies in comparative terms, a relentless furnace blazing for millions of years, yet burning out far more quickly than our gentle Sun. These stars live fast, die young, and their death throes, supernovae and hypernovae, send shock waves and heavy elements rippling across interstellar space, seeding future generations of stars and planets, including the atoms that make up everything you hold, breathe, and see. Notice how close yet distant they feel. The light reaching us tonight began its journey when civilizations on Earth were only in their infancy, and some may have already exploded. Their brilliance travelling silently through space, unseen, a ghostly echo of cosmic history. As you visualize these giants, allow yourself to feel the paradox of enormity and fragility. Their outer layers are so tenuous that a teaspoon of their material would weigh tons on Earth, yet they are held together by a delicate balance of gravity and radiation pressure, a struggle that defines their very existence. And while your body rests, let your mind wander through the convecting surfaces of these hypergiants, bubbles of superheated plasma rising, expanding and collapsing, each one larger than our entire solar system, a rhythm of creation and destruction repeating over decades, centuries or millennia. Tonight the universe is not a distant abstraction, it is alive in your imagination, pulsating, expanding, breathing. And while you drift, consider the gift these stars leave behind: carbon, oxygen, iron, gold, elements forged in their cores and cast across the galaxy, eventually becoming part of planets, water, and even you. You are, quite literally, made of stardust, remnants of giants that once burned brighter than entire neighborhoods of stars. Let this awareness calm you, soothe your mind, and expand your sense of scale. Because tonight, you are both witness and participant in the story of the universe, riding alongside stars that are bigger than your wildest dreams, and preparing to fall asleep with the gentle awe that only the cosmos can inspire. Have you ever imagined a star that seems alive, expanding and contracting like a colossal heartbeat? Tonight, you're about to drift alongside such giants, red supergiants whose surfaces swell with vast convection cells, each larger than the orbit of Mars, rising and falling as if the star itself were breathing. Betelgeuse, nestled in Orion's shoulder, is one of the closest examples. Its diameter stretches roughly 700 times that of our Sun, and if it were placed at the centre of our solar system, Earth, Mars, and even Jupiter would be swallowed by its outer layers. For us, this star is a point of reddish light, flickering subtly in the night sky, but its reality is a violent, pulsating furnace, slowly shedding material into space, feeding future generations of stars and planets. These pulses are not gentle, they are the outward signs of deep stability. The tug-of-war between gravity pulling inward and radiation pushing outward, a struggle that keeps the star alive yet slowly drives it toward its inevitable demise. Imagine standing on a planet nearby. The sky would never darken. A persistent crimson light would dominate, casting long, eerie shadows, a constant reminder of the star's power and scale. And yet, from Earth, this drama unfolds silently. Betelgeuse's dimming in recent years has stirred both awe and concern. as astronomers watched massive clouds of ejected material obscure parts of its light, reminding us that even stars this close to us are unpredictable, living entities in constant flux. Then consider the blue supergiants, like Rigel, Orion's other shoulder jewel. Far hotter than red supergiants, their blue-white brilliance tells a story of extreme temperature, fierce fusion, and a life lived at breakneck speed. While our sun burns steadily for 10 billion years, these giants consume their fuel in mere millions. Rigel, though younger than most stars we see in the sky, will exhaust its energy and explode as a supernova long before the sun reaches its twilight. And the contrast between red and blue giants is stark. One slow, massive, swelling over centuries, the other burning hot, fast, and violently, a fleeting blaze across cosmic time. Tonight, as you lie comfortably, imagine drifting through their stellar winds, feeling the pull of their gravity, sensing the hum of fusion in their cores, the gentle but terrifying scale of their existence. Their lives are short, brilliant, and transformative, leaving chemical legacies across the galaxy. Every carbon atom, every oxygen molecule, every bit of iron that will someday form worlds owes its existence to stars like these, giants that live fast and die in spectacular explosions. And as you drift towards sleep, allow yourself to marvel at their enormity, to feel small yet connected, and to let the gentle awe of the cosmos lull you into a deep, peaceful rest. These giants, invisible in their full grandeur to the naked eye, continue to shape the universe and the very atoms inside you, a silent reminder of the scale, beauty, and mystery that lies beyond our everyday perception. Far beyond the stars you recognize at the outer edges of the Milky Way exist hypergiants so enormous that they defy comprehension. V354 Cepheid, for example, stretches roughly 890 times the radius of our Sun, and if placed in our solar system, its outer layers would engulf Mercury, Venus, Earth, Mars, and Jupiter. These stars pulse, expand, and contract over cycles of years, shedding colossal amounts of material with every breath, is forming glowing shrouds of gas and dust that stretch for light years. The environment here is sparse, the galactic suburbs quiet, yet these giants have grown to sizes typically found in dense stellar nurseries. How did they reach such extremes so far from the crowded star-forming regions? Some drifted outward over millions of years, others may have formed in small clusters that dispersed, leaving them as lonely survivors. Each hypergiant is in the late stages of its life, fusing heavier and heavier elements in its core, and every new stage of fusion lasts less time than the last. Carbon burning may persist for 1,000 years, neon for a year, oxygen for months, and silicon for mere days. Each stage brings the star closer to its violent end, a supernova that will ripple through space and scatter elements that will one day become part of new stars and planets. Observing V354, Cepheid reminds us how unpredictable these giants are. They pulse with massive energy, expel their outer atmospheres, and yet remain stable enough to continue their slow demise. As you imagine this distant giant, picture standing at the edge of the solar system, looking up to see a crimson sphere dominating the sky, its glowing surface shifting and convecting, the scale almost impossible to grasp. Every pulse, every breath, sends elements outward, carbon, oxygen, iron, that will one day be woven into the universe. The star's life is a delicate balance between gravity and radiation pressure, a battle that will eventually fail, producing a supernova whose shockwave can trigger star formation in neighbouring clouds. And while it may be thousands of light years away, The legacy of such a hypergiant touches everything, from the smallest dust grain to the largest planets yet to form. As you drift into sleep, let your mind float across the galaxy, feeling the immensity of these giants, understanding that even in the quiet suburbs of space, forces far larger than life are at work, shaping the cosmos with every pulse, every contraction, every stellar breath. Deep within dense star clusters, dozens of massive stars crowd together in tight pockets of space, their combined energy lighting the surroundings like a city of suns. Westerland 1, one of the most extreme clusters in the Milky Way, hosts stars like Westerland 126, a red supergiant approaching hypergiant status with a radius potentially over 2,500 times that of our Sun. If placed at the center of our solar system, its outer layers would reach beyond Saturn, possibly toward Uranus, consuming every inner planet. In these clusters, stars interact gravitationally in intense and sometimes chaotic ways, occasionally exchanging material or even ejecting smaller stars at incredible velocities. The sheer density of these clusters means that the night sky on any hypothetical planet there would never darken. Dozens of brilliant stars would illuminate the landscape simultaneously, shifting colors as different giants rose and set. Westerland 126 is a young star, only about 4 to 5 million years old, yet it has already reached an advanced evolutionary stage, swelling into a red supergiant and beginning to shed mass at staggering rates. Its outer layers are blown off by radiation pressure, forming an enormous shell of gas and dust detectable across trillions of miles. Observing such a star challenges our understanding of physics. It sits near the theoretical Eddington limit, the boundary beyond which a star cannot grow without shedding material to maintain balance. Every ejection, every pulse of mass, is a reminder that stars are not static objects, but dynamic entities engaged in constant struggle with their own gravity and radiation. These processes seed the interstellar medium with elements essential for life, spreading carbon, oxygen, and iron across space, and leaving a chemical legacy that will endure long after the star itself explodes as a supernova. As you picture this star cluster in your mind, imagine the interplay of light, gravity and energy, a celestial dance both violent and mesmerizing. Let your imagination drift among these luminous hearts, feeling the pulse of their energy as it travels across the galaxy, shaping not just the environment around them but also the very building blocks of planets, life, and future generations of stars. And as you relax, let the enormity of these clusters expand your sense of scale, grounding you in the awe-inspiring reality that even the tiniest speck of dust you are made of once passed through the life cycle of stars far bigger than anything we can fully comprehend. Far beyond the familiar stars of our Milky Way lies the large Magellanic Cloud, a companion galaxy about 160,000 light-years away, where some of the most extreme stars ever discovered reside. Among them is R136A1, a blue hypergiant that defies ordinary imagination. Its mass exceeds 200 times that of our Sun, and its radius stretches over 2,000 times larger, meaning if it replaced our Sun, the entire inner solar system would vanish inside its outer layers. This star burns with unimaginable intensity, consuming its nuclear fuel at a pace that dwarfs the Sun's steady fusion. Each second releases more energy than millions of suns combined, a relentless inferno in the quiet darkness of its galaxy. Observing R136A1 is like peering into the heart of creation itself. It illuminates its surroundings, shaping nearby clouds of gas and dust, influencing the formation of other stars and scattering elements forged in its core across interstellar space. Blue hypergiants like this live fast and die young, often in just a few million years, ending in supernovae or even hypernovae whose shockwaves ripple across the galaxy. The light we see tonight began its journey when Earth was still in its formative stages, a reminder that even distant stars are intimately connected to our cosmic story. Imagine drifting through that distant sky, feeling the pulse of such energy, the scale of a star so massive that your mind struggles to contain it. And while your body lies in quiet stillness, consider that the elements in your own blood, the oxygen you breathe, the carbon in your cells, may have originated from stars like R136A1, scattered across the universe by violent explosions. As you let your mind float across these intergalactic distances, allow the awe of scale, the intensity of energy, art, and the story of cosmic life and death to wash over you, slowing your heartbeat, widening your perspective, and guiding you gently towards sleep. In this quiet journey, the universe becomes a living, breathing expanse, each hypergiant a pulse in the endless rhythm of creation, teaching us about the impermanence, power, and majesty of the cosmos while lulling you into peaceful wonder. Not all giants reveal themselves easily. Many of the largest stars hide behind thick veils of dust and gas, their true scale invisible to ordinary telescopes. NML Cygni, for example, sits about 5,300 light-years away and is wrapped in an enormous shell of ejected material that obscures most of its light. Its radius ranges between 1,100 and 1,600 times that of our Sun, meaning if placed at the center of our solar system, the inner planets and even Jupiter would be engulfed by its outer layers. This hypergiant is not static. It pulses slowly over cycles of roughly 1,000 days, each pulse driving massive quantities of material into space, expanding its surrounding nebula. The star's outer atmosphere is tenuous, held together precariously by gravity, while radiation pressure pushes outward, creating a turbulent, leaking giant that cannot stop bleeding. Imagine floating near such a star. The sky would be dominated by a crimson shifting light, ever changing as the star breathes, expands and contracts. Every ejection carries elements forged in the star's core: carbon, oxygen, iron, seeding the galaxy for future generations of stars and planets. The hidden nature of NML Cygni reminds us that the universe is filled with surprises, with enormous objects quietly shaping space from the shadows. Observing it challenges our perception. Brightness alone is misleading. Distance masks reality, and the true giants often reside where we cannot easily see them. As you lie quietly, let your mind drift to this distant veiled star, feeling its slow pulses echo across light years, understanding that even hidden giants leave their mark on the cosmos, leaving a legacy of elements and energy that will eventually find its way into worlds yet to be born. The universe is vast, mysterious, and alive with motion, and stars like NML Cygni teach us that not all brilliance is immediately visible, yet all influence is profound. In the dense heart of the Milky Way, near the bright center of our galaxy, lurks a star slowly disassembling itself. Orviex Sagittarii is a red hypergiant about 1,520 light-years away, its radius reaching approximately 1,520 times that of the Sun. If placed in our solar system, its outer layers would extend past Saturn, swallowing Mercury, Venus, Earth, Mars, and Jupiter, leaving nothing but cosmic ash. but its size is only part of the story. VX Sagittarii is leaking mass at an astonishing rate, shedding roughly 1 Earth's worth of material every couple of months. Over centuries, this star expels enough matter to build entire small worlds, its outer atmosphere forming a luminous halo visible in infrared and radio wavelengths. The star pulses irregularly, driven by deep convection patterns where superheated material rises from the core to the surface and back, creating a rhythm both violent and mesmerizing. The surrounding region is crowded with stars, gas clouds, and other massive objects amplifying the influence of VX Sagittarii's outpouring. Every burst, every ejection carries heavy elements, carbon, oxygen, silicon, iron, that enrich the interstellar medium, seeding the next generation of stars and planets. Imagine floating near such a star. The sky is awash with red light, the pulsation sending waves of energy through space, the star alive yet disintegrating before your eyes. This is the paradox of hypergiants, immense, powerful, and yet fragile, existing at the edge of stability, destined to end in a spectacular supernova. As you drift in your bed, allow yourself to feel the scale, the energy, and the slow, inevitable decay of a star so massive, so vibrant, and so fleeting. Each heartbeat of VX Sagittarii echoes across light years, reminding us that the universe is not static. It breathes, it evolves, and it leaves traces of its grandeur for those willing to witness, even in quiet contemplation before sleep. Far across the dark expanse of the night sky, in the constellation Canis Major, lies one of the most extreme stars ever observed, V Canis Majoris. Its scale defies ordinary imagination, a red hypergiant so vast that if it replaced our Sun, the inner planets, including Mercury, Venus, Earth, Mars, and the asteroid belt, would be completely engulfed, leaving only the outer ice giants barely surviving on the fringes. Estimates of its radius have varied widely over decades, from nearly 2,000 times that of our Sun to more conservative modern figures of approximately 1,300 to 1,700 solar radii. Yet even the lowest estimate is staggering beyond comprehension. So V Canis Majoris is not only enormous in size but also incredibly luminous, pumping out roughly 270,000 times the energy of the Sun, mostly in the infrared spectrum, making much of its brilliance invisible to human eyes. Its outer atmosphere is tenuous, almost ghostly, with material constantly peeling away in irregular bursts, forming a complex nebula of gas and dust that twists and swirls around the star like an intricate cosmic sculpture. The violent convection patterns deep within its interior create massive bubbles of plasma that rise to the surface, explode outward, and sink back down, each one comparable in size to our entire solar system, a rhythm of energy and motion that repeats over years and decades. These bursts and convective eruptions are not merely aesthetic, they carry heavy elements forged in the star's core, carbon, or oxygen, silicon, iron, into the surrounding interstellar medium, seeding the galaxy with the essential ingredients for new stars, planets, and potentially life. Observing V Canis Majoris reminds us of the paradoxical nature of hypergiants, immense, radiant, and powerful, yet precariously balanced against the forces that threaten to tear them apart. Gravity struggles to hold the tenuous outer layers in place, while radiation pressure pushes outward relentlessly, creating an unstable equilibrium that will ultimately fail when the star reaches the end of its life. One day, possibly within the next few 100,000 years, V Canis Majoris will explode as a supernova, an event so bright that it could be visible from Earth even during daylight, illuminating the surrounding sky and forever altering the constellation in which it resides. Until that moment, the star continues its slow but dramatic disassembly, a living testament to the extreme possibilities of stellar physics. As you lie in quiet reflection, let your mind drift across the cosmic distances separating us from this titan, imagining its immense surface, the glowing convection cells, the shifting nebula, and the relentless forces at play. Feel the calm and awe of contemplating such a gargantuan object, understanding that every atom of heavy elements in your body may trace its origins to stars like Canis Majoris, expelled into space in bursts of energy that ripple across light years. Allow the scale, beauty, and violence of this hypergiant to expand your perspective, slowing your heartbeat, stretching your imagination, and carrying you gently into the meditative calm that only the universe can inspire before sleep. Far across the galaxy, roughly 20,000 light-years away in the constellation Scutum, sits Stevenson 2-18, the current confirmed record holder for the largest known star. A red supergiant, possibly a hypergiant, its radius stretches approximately 2,150 times that of our Sun, so vast that light takes nearly 9 hours to cross from one side to the other. If placed at the centre of our solar system, its outer layers would extend well beyond Saturn, possibly approaching Uranus, swallowing Mercury, Venus, Earth, Mars, and the asteroid belt entirely. Despite its immense size, its mass is only 20 to 40 times that of the Sun, here highlighting the incredibly low density of these hypergiants, mostly empty space enveloping a dense core where fusion drives the star's brilliance. Stevenson 2-18 emits energy equivalent to roughly 440,000 suns, almost entirely in the infrared spectrum, making much of its glow invisible to human eyes but detectable with modern instruments. Situated within a rare cluster of about 24 other red supergiants, Stevenson 2-18 is a survivor of a massive star-forming event approximately 20 million years ago, the largest and most luminous of its siblings. Its evolutionary stage places it in the late phases of life, having burned through nearly all its hydrogen fuel and now fusing heavier elements in shells surrounding the core. The carbon-burning phase may last hundreds of years, neon a single year, oxygen months, and silicon only days, is accelerating toward the inevitable supernova. When that moment arrives, it may not be a typical supernova but a hypernova, briefly outshining the Milky Way and sending shock waves across thousands of light years, compressing interstellar gas and triggering the birth of new stars. The sheer scale of Stevenson 2-18 challenges every intuition about stars, a living laboratory for understanding the physics of extreme luminosity, radiation pressure, and mass loss. The outer layers are tenuous and constantly shed into space, a process that both limits growth and seeds the surrounding medium with heavy elements like carbon, oxygen, and iron, essential for planetary formation and life elsewhere. Observing this star forces one to confront the vastness and fragility of the cosmos, reminding us that even the most massive structures are ephemeral, yet governed by delicate balances between gravity and radiation. As you imagine Stevenson 2-18, its immense surface, the slow convective motions of its outer layers, and the invisible energy radiating across light years, allow yourself to feel the quiet awe and perspective this star offers. Even as its life nears its cataclysmic end, the star continues to shape the galaxy, leaving a legacy of elements and energy that will persist long after its light reaches us. Let this vision expand your sense of scale, instilling both wonder and serenity, guiding your mind gently toward rest while contemplating one of the largest, most extreme stars the universe has ever produced. Every star has a limit, a boundary beyond which it cannot grow without tearing itself apart. This boundary is known as the Eddington limit, or a theoretical maximum where the outward pressure from a star's radiation equals the inward pull of gravity. For stars like Stevenson 2-18, this limit defines the upper edge of possible size, explaining why even the largest red hypergiants stop at around 2,000 to 2,500 solar radii. Beyond this point, the intense radiation generated by nuclear fusion in the core would blow away the outer layers faster than gravity could retain them, preventing further expansion. The Eddington limit is not just a number. It represents the fundamental balance that governs the life and death of massive stars. When a star approaches this threshold, its outer atmosphere becomes unstable, pulsating violently, shedding vast clouds of gas and dust, and creating nebulae that can stretch for light years. These expelled materials carry the products of nuclear fusion, carbon, oxygen, iron, into space, enriching the interstellar medium and setting the stage for future star and planet formation. The limit also explains why stars larger than Stevenson 2-18 are so rare. In the early universe, with gas composed mostly of hydrogen and helium, conditions allowed the formation of quasi-stars and other hypothetical giants that could exceed today's constraints. But modern chemistry and physics impose stricter boundaries. Understanding the Eddington limit provides insight into the delicate interplay of forces that sustain a star for millions of years, and ultimately dictate the spectacular events of supernovae and hypernovae. As you imagine lying beneath the night sky, consider that each star you see is contained by these cosmic rules, and their massive size balanced on the knife edge of physics. The outer layers you cannot see are constantly fighting to remain intact, a dynamic tension between creation and destruction. This knowledge adds depth to your perception of the cosmos, highlighting the fragility behind the apparent power of the universe's most extreme objects. Every pulse, every mass ejection, every flicker of luminosity is a testament to the constant struggle against the Eddington limit, a struggle that shapes the structure, life, and eventual death of the largest stars known. And as you drift towards sleep, allow the enormity of these forces, invisible yet omnipresent, to expand your imagination, bringing both awe and a quiet sense of peace in the knowledge that even the largest giants obey rules, and that these rules, in turn, create the universe we can understand, explore, and dream about. While red hypergiants like Stevenson 2-18 and Canis Majoris dominate in sheer size, blue hypergiants tell a different story, one of extreme energy, scorching heat, and breathtakingly brief lifespans. Stars like R13601 in the Large Magellanic Cloud burn at surface temperatures exceeding 40,000 degrees Fahrenheit, radiating millions of times the sun's luminosity. Unlike the slow, pulsing red giants, these blue behemoths consume their hydrogen fuel with astonishing speed, exhausting millions of years' worth of energy in just a few million. Their light is so intense it sculpts the surrounding nebulae, ionizing gas clouds, and shaping the birth of nearby stars. Blue hypergiants are often unstable, losing mass at incredible rates through powerful stellar winds that carry thousands of solar masses over their short lifetimes. Their immense radiation pressure pushes outward, while gravity struggles to maintain structural integrity, creating violent surface activity and irregular pulsations. Observing these stars from Earth, they appear as bright, steady points of blue-white light, yet each flicker and shift tells a story of extreme fusion deep within, a furnace at the heart of the star working at a speed the sun could never match. These giants live fast and die young, destined to end in catastrophic supernovae or hypernovae, dispersing the heaviest elements into space, elements that form planets, atmospheres, and eventually the building blocks of life. Imagine drifting near one of these stars, the sky dominated by searing blue brilliance, the airless void filled with radiation so intense it shapes matter itself. Even at thousands of light-years away, their influence reaches across interstellar space, reshaping stellar nurseries and leaving chemical fingerprints that will persist for billions of years. For you, lying quietly in your bed, the existence of such stars is both humbling and awe-inspiring. They embody the extremes of physics and nature, demonstrating how life, energy, and destruction are intertwined on a cosmic scale. Each second in a blue hypergiant's life is a million-fold increase over the sun's output, yet fleeting in cosmic terms. Their violent yet orderly existence reminds us of the fragile balance that allows even the largest objects to persist, creating a rhythm of creation and destruction that echoes across the galaxy. As you let your mind drift, picture the furious, radiant blue giants alive in the distant universe, burning hot and bright, shaping everything around them while preparing to leave behind their indelible mark on space, energy, and matter, a reminder that the cosmos is vast, dynamic, and endlessly mesmerizing as you fall into sleep. Beyond the blinding heat of blue hypergiants, red hypergiants move through the galaxy with a slow, deliberate majesty, concealing a turbulent inner life beneath their seemingly calm surfaces. Stars like Musaphei, also known as the Garnet Star, shine deep crimson in the night sky, a visual testament to their relatively cooler surface temperatures of around 6,300 degrees Fahrenheit. Yet their sheer size radiates enormous amounts of energy. Musaphei's radius stretches roughly 1,400 times that of our Sun, so vast that if placed at the center of the solar system, it would engulf Mercury, Venus, Earth, Mars, and Jupiter. But this star is far from tranquil. Its outer layers pulse irregularly, expanding and contracting over cycles that can last from 2 to 12 years. Each pulse releases tremendous amounts of energy and ejects streams of gas into the surrounding space, forming a glowing envelope of dust that gradually drifts outward. Observing these stars reminds us that red hypergiants are living, breathing entities on a cosmic scale. The material they shed enriches the interstellar medium with carbon, oxygen, and heavier elements, providing the raw ingredients for future stars and planets, although even for worlds that may eventually harbour life. Despite their colossal size, the density of their outer layers is extremely low. A teaspoon of gas from Musaphei's atmosphere would weigh far less than air on Earth. Deep inside, however, the core is compressed to extraordinary densities, sustaining nuclear fusion that powers the star's slow, pulsing heartbeat. Over time, these giants approach the end of their lives, with each new stage of fusion, helium, carbon, neon, oxygen, silicon, lasting progressively shorter periods, culminating in a dramatic supernova that scatters the remaining elements across light years. While the visual spectacle from Earth is muted by distance and dust, infrared observations reveal the true scale of their luminosity, offering glimpses into processes invisible to the naked eye. As you imagine Musaphei, let your mind drift across its immense breathing surface, the shifting clouds of gas, the slow undulations of its outer layers, and the colossal forces at work beneath. The star's grandeur is silent yet powerful, a reminder of the extraordinary scales at play in the universe, And as you settle into quiet reflection, allow yourself to feel the calm awe inspired by witnessing the secret lives of red hypergiants, their slow rhythms guiding your imagination into the quiet serenity of sleep. Hidden deep in the constellation, Cepheus lies V Cephei, a red hypergiant whose extreme size and unusual behavior make it one of the most fascinating stars in our galaxy. Its radius is estimated between 1,000 and 1,600 times that of our Sun, so massive that if it replaced our Sun, the inner planets, including Earth, would be swallowed entirely, with only the farthest planets remaining on the edges. V Cephei is not alone. It has a companion star, a smaller but still massive blue star, orbiting within or grazing the outer layers of the giant during its 20-year orbit. This unusual configuration causes dramatic and observable variations in brightness as the two stars interact, stirring up vast streams of gas and creating shock waves that ripple through the hypergiant's atmosphere. The outer envelope of V Cephei is extremely tenuous, so loosely held that if you could scoop a chunk from it, the gas would feel thinner than a vacuum chamber on Earth. Inside, however, the core remains intensely dense, fusing heavier elements at tremendous pressures and temperatures. Each orbital pass of the companion disrupts the outer layers, causing violent ejections of material that feed a surrounding nebula, glowing in infrared wavelengths and stretching for trillions of miles across space. These interactions illustrate how dynamic and unstable hypergiants can be, living on the edge of physical limits. V Cephei is also nearing the final stages of its life. As hydrogen fuel runs low and heavier elements are fused, the star becomes increasingly unstable. Each pulse and mass ejection brings it closer to a cataclysmic supernova, an explosion that will illuminate the galaxy and disperse enriched elements that will seed future stars and planetary systems. Imagine drifting near V Cephei, the sky dominated by a massive red sphere, turbulent and alive, a companion star slicing through its outer layers, sending shocks and energy rippling outward. For observers on Earth, now we see a faint point of light, yet the reality is a living, chaotic giant, breathing, convecting and shedding itself into space. As you lie quietly, allow your mind to travel to V Cephei, following the enormous pulses, the dense core's relentless fusion, and the companion's dramatic orbit. Feel the scale, the turbulence, and the beauty of one of the most extreme stellar systems in our galaxy, letting the imagination expand while your body relaxes, preparing you for deep, cosmic-inspired sleep. Far across the Milky Way, hidden behind dense clouds of interstellar dust, lies NML Cygni, a red hypergiant so massive and luminous that it defies ordinary comprehension. Its radius ranges between 1,100 and 1,600 times that of our Sun, meaning if it replaced the Sun at the center of the solar system, Mercury, Venus, Earth, Mars, and even Jupiter would be engulfed entirely, leaving the outermost planets barely on the edges of its enormous envelope. NML Cygni is largely invisible to the naked eye due to the thick shell of dust and gas surrounding it, but modern infrared and radio observations reveal the magnitude of its existence. This dust cocoon is not merely decorative, it is composed of material ejected from the star itself, thrown off in massive quantities over thousands of years. The star pulses over cycles of roughly 1,000 days, with smaller variations layered atop the long-term cycle, and each pulse drives more material into the surrounding space. These ejections enrich the galaxy with heavy elements like carbon, oxygen, and iron, creating the building blocks for future stars, planets, and potentially life. ReNML. Cygni sits within the Cygnus OB2 association, a stellar neighbourhood of massive young stars, yet it is one of the oldest residents, having aged far more quickly due to its enormous size and rapid consumption of fuel. Its outer layers are tenuous, barely held together by gravity, while the core continues to fuse increasingly heavy elements, moving from helium to carbon, neon, oxygen, and silicon in a progression that shortens with each stage. The star is in a constant state of instability, and each pulse or ejection subtly reshapes the surrounding nebula, creating a lopsided dynamic envelope that glows in infrared wavelengths, giving us a glimpse into its ongoing transformation. As you imagine NML Cygni, picture standing at the edge of its atmosphere, looking out across a glowing fog of ejected gas stretching trillions of miles, sensing the slow rhythm of its pulses and the invisible forces of radiation pressure and gravity battling to maintain the star's structure. Despite being distant, its influence is profound. The material it expels will mix with interstellar clouds, seeding the galaxy with the elements necessary to form planets, moons, and the potential for life elsewhere. NML. Cygni's silent power is a reminder that the most extreme objects in the universe often operate beyond our perception, quietly shaping cosmic history while remaining hidden in the darkness. Lying in your bed, imagine the gentle yet relentless rhythm of this star, the slow breathing of a cosmic giant, and let the sense of scale, power, and quiet mystery wash over you. The universe is alive with these enormous hidden stars, each one a furnace of energy, and is shaping the very matter that eventually becomes part of planets, atmospheres, and even you. Allow this image to expand your sense of wonder, grounding your mind in the enormity of the cosmos while carrying you gently into a deep, reflective sleep, inspired by the quiet life of one of the Milky Way's most secretive giants. In the crowded, energetic heart of the Milky Way, near the bright Sagittarius constellation, lies VX Sagittarii, a red hypergiant whose scale and activity are as dramatic as they are mesmerizing. Sitting approximately 1,520 light-years from Earth, VX Sagittarii reaches a radius of roughly 1,520 times that of our Sun. If it were placed at the center of our solar system, Mercury, Venus, Earth, Mars, and even Jupiter would be engulfed within its outer layers, leaving the outermost planets on the fringes. But size alone does not convey the full story. VX Sagittarii is in a constant state of evaporation, losing mass at astonishing rates, about one Earth's worth every few months. This relentless shedding creates a luminous envelope of gas and dust, hundreds of times wider than the star itself, glowing in infrared and radio wavelengths and slowly drifting across interstellar space. The star pulses irregularly, driven by superheated material rising from its core to the surface and falling back, creating massive convection patterns that are almost impossible to imagine in scale. Each pulse, each burst of mass loss, contributes to a larger cycle of cosmic recycling. Heavy elements such as carbon, oxygen, silicon, and iron are expelled into surrounding space, eventually forming the building blocks for new stars, planets, and even life. VX Sagittarii exists in a densely packed galactic environment where gravitational interactions with nearby stars and gas clouds amplify the effects of its mass loss. The star's core, intensely compressed, continues fusing heavier and heavier elements, moving through successive stages of fusion: helium burning, carbon, neon, oxygen, and silicon, with each stage shorter than the last accelerating the star toward its inevitable demise. When VX Sagittarii finally ends its life, it will explode as a supernova, a brilliant, violent event that will briefly outshine its surrounding region, sending shock waves through nearby gas clouds and triggering the formation of new stars. Imagine drifting near this hypergiant, the crimson surface glowing, shifting, pulsing, and shedding enormous streams of material, a living, dynamic entity sculpting its corner of the galaxy. The star is a paradox, immense yet fragile, destructive yet creative, a furnace shaping both the present and future of the Milky Way. For you, lying quietly, let this vision expand your imagination, allowing the scale, energy, and elegance of VX Sagittarii to lull you into contemplation and calm. Sense the slow rhythm of its pulses, the delicate balance of forces holding the star together, and the cosmic legacy it leaves behind. Every atom in the material it ejects, every particle of dust forming its halo, is part of a story billions of years in the making. As your mind drifts across light years to this evaporating giant, allow yourself to feel the majesty, power, and serenity of a star at the extreme edge of existence, gently carrying you into sleep while the universe quietly continues its vast, intricate dance. In the southern constellation Canis Major, a colossal red hypergiant dominates the cosmic landscape, Canis Majoris. For decades, it held the title of the largest known star in the universe, a true titan of stellar evolution. Its radius, estimated between 1,300 and 1,700 times that of our Sun, is so vast that if placed at the center of our solar system, Mercury, Venus, Earth, Mars, and even Jupiter would be swallowed entirely. Despite this enormous volume, its mass is only about 20 to 40 times that of the Sun, highlighting the incredibly low density of its outer layers. Its surface is tenuous and volatile, peeling away in irregular bursts driven by massive convection cells that rise from the core, explode outward, and sink back down, then each roughly the size of the solar system itself. These convective eruptions send streams of gas and dust into surrounding space, forming intricate nebulae visible in infrared imaging and enriching the interstellar medium with heavy elements forged deep within: carbon, oxygen, silicon, and iron. Canis Majoris is slowly dimming over time as these ejections accumulate in its surrounding nebula, absorbing more of the star's light before it can escape to Earth. Its core, however, remains a furnace of nuclear fusion, fusing heavier elements and edging steadily toward its inevitable supernova. When that moment arrives, the explosion will be catastrophic, releasing more energy in a few seconds than the Sun will produce over its entire 10 billion year lifespan. Yet even in its death, Canis Majoris will continue to shape the cosmos, dispersing its enriched matter across thousands of light years and seeding the next generation of stars and planets. As you imagine this star, consider its turbulent outer layers, the immense power of its core, and the delicate balance of forces that have allowed it to exist for millions of years. Its surface breathes, its energy pulses, and every ejected particle becomes a potential seed for future worlds. For anyone lying quietly and allowing their mind to drift, visualizing Canis Majoris is a lesson in scale, power, and cosmic rhythm. Its quiet yet violent presence reminds us that the universe is not static. It is dynamic, ever-changing, and filled with forces far beyond human comprehension. As you settle into your thoughts, picture the massive nebulae, the flowing gas, the simmering core, and let the enormity of this hypergiant both humble and calm your mind. carrying you into a reflective, meditative state where the universe's silent giants lull you gently towards sleep. Far across the Milky Way, in the constellation Scutum, Stevenson 218 reigns as the largest confirmed star in our galaxy, a red supergiant whose sheer scale pushes the boundaries of physics. Its radius stretches approximately 2,150 times that of our Sun, and if placed at the centre of our solar system, the outer layers would extend past Saturn, possibly nearing Uranus, engulfing Mercury, Venus, Earth, Mars, and the asteroid belt entirely. Despite this mind-boggling volume, its mass is only 20 to 40 times that of the Sun, a testament to how hypergiants are mostly empty space with dense cores sustaining the nuclear fusion that powers them. Where Stevenson 218 emits energy equivalent to roughly 440,000 suns, almost entirely in the infrared spectrum, revealing how much of its brilliance is invisible to the naked eye, yet critical in shaping its surroundings. Situated within a rare cluster of red supergiants, it is the largest and most luminous, a survivor of a massive star-forming event around 20 million years ago. Its evolutionary stage is extreme. Hydrogen has been mostly consumed, and the star now fuses heavier elements in successive shells around the core: helium, carbon, neon, oxygen, and silicon, with each stage progressively shorter in duration. The carbon-burning phase may last hundreds of years, neon around a year, oxygen months, and silicon only days. The outer layers of Stevenson 218 are tenuous and constantly shed into space, forming vast nebulae that carry the star's heavy elements across light years, enriching the interstellar medium and enabling future star and planet formation. Observing Stevenson 2-18 highlights the delicate balance that sustains hypergiants. Gravity struggles to contain the outer layers, while radiation pressure pushes outward, creating pulsations, convection, and mass ejections that define the star's dynamic existence. Its fate is inevitable. When it reaches the end of its life, it may produce a hypernova, a catastrophic explosion far brighter and more energetic than a standard supernova, sending shockwaves across thousands of light years, sculpting the galaxy and dispersing elements crucial for planetary and biological evolution. As you imagine this giant, consider the immense, slowly breathing surface, the turbulent outer envelope, and the nuclear furnace at its core. Each pulse and ejection is a reminder of the cosmic forces at play, and as your mind drifts through this vast scale, allow yourself to feel both humility and awe. The enormity of Stevenson 2-18, its power and its impermanence can soothe and inspire, grounding your imagination in the grandeur of the universe while gently guiding you toward a deep, restful sleep. Even the largest stars are not limitless. Their size and structure are constrained by the fundamental laws of physics. The Eddington limit defines the maximum luminosity a star can achieve before radiation pressure overcomes gravity, effectively capping how massive and how large a star can grow. Stars like Stevenson 2-18 sit near this boundary. Their immense energy output balance precariously against the gravitational forces that hold them together. If a star exceeds the Eddington limit, its outer layers are blown away in massive stellar winds, stripping material into space and forming vast envelopes of gas and dust that can extend for light years. This self-regulating mechanism explains why hypergiants rarely exceed around 2,000 to 2,500 solar radii under current cosmic conditions. In the early universe, when gas was primarily hydrogen and helium, conditions allowed for even larger stars such as quasi-stars, which could surpass today's limits due to different chemical compositions and internal structures. The Eddington limit is more than a theoretical concept. It is a dynamic boundary that governs the life cycles of massive stars. As a hypergiant approaches this threshold, it experiences increasing instability. Its outer layers pulse violently, convective cells rise and collapse, and enormous quantities of matter are expelled into space. These ejections carry heavy elements, carbon, oxygen, iron, into the galaxy, seeding the material for future stars, planets, and the chemistry of life itself. Observing stars near the Eddington limit provides insight into the extreme conditions that dictate the evolution, luminosity, and eventual death of hypergiants. The interplay between radiation pressure and gravity shapes not only their structure, but also the environment around them, influencing star formation and galactic chemistry across thousands of light years. Lying quietly, imagine yourself drifting near such a star, sensing its outer layers trembling under immense forces, feeling the subtle rhythm of expansion and contraction, the convection currents carrying energy from the core to the surface, and the streams of ejected material radiating into space. The Eddington limit is a reminder that even the universe's largest objects are governed by rules, and that their beauty, power, and eventual demise are orchestrated by physics on a scale almost impossible to comprehend. Let this knowledge expand your sense of wonder, grounding your imagination in the structure and balance of the cosmos while guiding you gently toward a peaceful, reflective sleep. While red hypergiants like Stevenson 2-18 and Canis Majoris impress with their immense size, blue hypergiants teach us about the extremes of energy and life lived in overdrive. Stars such as R136A1, located in the Large Magellanic Cloud, must burn at temperatures exceeding 40,000 degrees Fahrenheit, radiating millions of times the sun's energy. Unlike red giants, which expand slowly and pulse over years or decades, blue hypergiants consume their nuclear fuel at astonishing rates, living fast and dying young. A star 10 times the sun's mass may last only 30 million years, while one 40 times larger, like R136A1, may burn through its fuel in mere millions of years. Their surface is turbulent, driven by extreme convection and radiation pressure, expelling material into surrounding space in the form of powerful stellar winds. These winds carry thousands of solar masses worth of elements, enriching the interstellar medium with carbon, oxygen, and heavier elements essential for future star and planet formation. The light from these giants sculpts nearby gas clouds, thus ionizing hydrogen and influencing the formation of neighboring stars, creating a dynamic environment where energy, gravity, and matter interact on scales almost impossible to comprehend. Observing these stars from Earth, they appear as small blue-white points of light, yet each flicker represents immense internal forces and furious activity within. The life of a blue hypergiant is a race against time, a brief blazing existence compared to the steady 10 billion year life of a star like our Sun. When their fuel runs out, they end violently, exploding as supernovae or hypernovae, sending shock waves and heavy elements across thousands of light years, shaping the chemical composition of galaxies and leaving behind neutron stars or black holes. Imagine floating near one of these stars. The searing blue light dominates the sky, and the energy radiates outward in all directions, transforming the environment around it, influencing future generations of stars and planetary systems. As you lie quietly, let your mind drift across these extreme stellar furnaces, feeling the immense power, the rapid rhythm of life and death, and the profound influence of a single star on the galaxy. These hypergiants, although brief in cosmic terms, demonstrate the universe's capacity for both creation and destruction, reminding us of the extraordinary forces at play while gently lulling your imagination into a state of awe and restful contemplation. Long before galaxies and planets formed, in the universe's first few 100 million years, extraordinary stars existed that dwarfed anything alive today. Quasi-stars were hypothetical giants, yet are powered not only by nuclear fusion but by a black hole at their core. These black holes fed on surrounding matter, releasing energy that supported the massive stellar envelope and prevented collapse. Estimates suggest quasi-stars could reach diameters of 50,000 to 100,000 times that of our Sun, encompassing hundreds of entire solar systems within a single star. The immense energy from the central black hole created outward radiation pressure that balanced gravity over a lifespan of around 7 million years, a fleeting but monumental existence. From the surface of a quasi-star, our entire solar system would appear as a tiny fraction of the outer envelope, immersed in a sea of glowing gas and turbulence. These stars burned for only a few million years, yet in that short time they forged conditions for the growth of supermassive black holes, seeding the centers of galaxies with the gravitational anchors that would persist for billions of years. Their outer layers eventually blew away as radiation overwhelmed the envelope, leaving behind the black hole that had powered them. Though quasi-stars no longer exist, their legacy is seen in the supermassive black holes at the centers of galaxies, including Sagittarius A star in the Milky Way, which contains 4 million solar masses. Imagining a quasi-star in its prime is almost impossible. A living, breathing entity larger than anything in today's universe, a combination of extreme gravity, immense size, and unimaginable energy. Each theoretical quasi-star illustrates the potential scale and variety of stellar objects in the early cosmos, providing insight into how the first galaxies could form and evolve. As you imagine drifting near one, the sheer vastness and the interplay of forces from core to surface inspires awe, highlighting the immense power and fragility of the universe's earliest giants, guiding the mind into quiet reflection while gently preparing for sleep. Beyond quasi-stars, cosmologists theorize the existence of dark stars, objects powered not by nuclear fusion but by dark matter annihilation. In the very early universe, regions dense with dark matter could have created stars thousands or even millions of times larger than modern hypergiants. These stars, composed mainly of hydrogen and helium, relied on energy released by the annihilation of dark matter particles at their cores, producing a slow, steady outward radiation pressure that held the immense outer envelope intact. Unlike conventional stars, dark stars would have had relatively cool surfaces despite their enormous sizes, potentially allowing them to reach millions of solar radii, making them larger than the entire stellar neighborhoods. Their immense mass and low-density outer layers would have created conditions where light traveled for days across the star's diameter, with pressure waves and radiation moving so slowly that the star behaved almost like a loose cluster of glowing gas rather than a coherent, compact object. The slow, steady energy from dark matter could have allowed these stars to survive hundreds of millions or even billions of years, far longer than typical massive stars. When their dark matter fuel ran out, they would collapse, some potentially igniting nuclear fusion briefly, or leaving behind massive black holes that would seed the centers of future galaxies. Dark stars, though entirely hypothetical, illustrate the extreme possibilities of stellar physics and the unknown potential of the early universe. Their massive envelopes, low densities, and reliance on dark matter create a vision of stars beyond ordinary comprehension, where the universe itself becomes a laboratory for structures larger and more complex than anything observed today. Lying quietly, imagining a dark star allows your mind to wander across the early cosmos, seeing enormous, almost invisible giants slowly shaping the universe. Their existence, though unconfirmed, challenges our understanding of size, energy, and the mechanics of star formation, meander, offering a profound sense of scale and wonder, while gently guiding your thoughts toward calm, cosmic-inspired sleep. Long before the familiar stars of the modern Milky Way, the universe was a dark, silent expanse filled primarily with hydrogen and helium. In this emptiness, the first stars, known as population 3 stars, ignited, blazing with unmatched intensity. These stars were massive, some reaching hundreds to possibly over 1,000 times the mass of our Sun, and they lived extraordinarily short lives, burning through their fuel in just a few million years. Unlike modern stars, they contained no heavy elements, which meant their formation, behavior, and luminosity were unlike anything we observe today. Population 3 stars were incredibly hot, their surfaces exceeding 50,000 degrees Fahrenheit, as radiating immense amounts of ultraviolet light that ionize surrounding gas, transforming the universe from opaque to transparent and initiating the era of reionization. Their nuclear furnaces created the first heavy elements, carbon, oxygen, silicon, and iron, which were later dispersed into space when these stars ended their lives in violent supernovae, enriching the interstellar medium for subsequent generations of stars and planets. From our perspective, these stars existed so long ago that their light has travelled for over 13 billion years to reach us, if any of it remains visible at all. Imagine standing near one, a towering, brilliant blue-white giant consuming its fuel with furious speed, casting intense ultraviolet radiation across a nascent universe, shaping the chemistry, structure, and evolution of the earliest galaxies. And a population 3 stars were ephemeral yet transformative, producing the first elements essential for planets, oceans, atmospheres, and ultimately life. Every atom of carbon in our bodies, every drop of oxygen, traces its origin to the cause of these first giants. Lying quietly, envision these colossal early stars igniting the darkness, each a transient but powerful source of energy that redefined the universe. Let the mind drift through the primordial cosmos, feeling the scale, heat, and influence of these extraordinary pioneers while embracing a calm, meditative state that prepares you for deep, restorative sleep. Some of the most massive population 3 stars and extreme hypergiants in the modern universe meet an ending unlike any typical supernova. Known as pair-instability supernova, these explosions occur when a star exceeds roughly 130 solar masses, creating conditions so extreme that photons in the core convert directly into matter-antimatter pairs. This process robs the star of radiation pressure, allowing gravity to overwhelm the core, triggering a catastrophic collapse. Temperatures and pressures rise rapidly, igniting explosive fusion of oxygen, silicon, and other elements all at once. The result is a star utterly destroyed, leaving no core, no neutron star, no black hole, just an expanding cloud of enriched debris. SN 2006 GY is a famous candidate, visible across hundreds of millions of light-years, representing the complete annihilation of a star many times the Sun's mass. These explosions seed the surrounding space with massive amounts of heavy elements, influencing star formation across hundreds of light-years and shaping the chemical evolution of galaxies. Imagine witnessing such a cataclysm. A star disappearing entirely in a brief instant, its material racing outward at thousands of miles per second, creating a luminous bubble that will expand and cool over millennia. For the first-generation stars, these pair-instability supernovae were essential, distributing the universe's earliest carbon, oxygen, and iron into the cosmos. As you lie quietly, envision the totality of a star vanishing, the brilliance, energy, and material it leaves behind rippling through the void. This understanding reminds us of the delicate, violent, yet profoundly creative forces that govern stellar life and death. The universe is alive with extremes. Beyond contemplating such destruction and creation together gently stretches your imagination, filling it with awe and preparing the mind for restful, cosmic-inspired sleep. Among the deaths of the most massive stars, hypernovae represent the absolute extreme of stellar destruction. When a hypergiant star, often rapidly spinning and exceptionally massive, reaches the end of its life, its core collapses with unimaginable force, releasing energy far beyond that of ordinary supernovae. These explosions can outshine entire galaxies for a brief period, sending shock waves across hundreds of light years and shaping the formation of new stars in surrounding clouds of gas and dust. Hypernovae are not merely bright, they generate focused gamma-ray bursts, narrow beams of high-energy radiation shooting from the poles of the collapsing star. Yet, if one of these jets were directed toward a planet within hundreds of light years, it could strip away the atmosphere and sterilize the surface completely. Fortunately, the geometry of such jets makes direct hits extremely rare. The material expelled by hypernovae is enriched with heavy elements, far more than standard supernovae can produce, contributing significantly to the cosmic abundance of elements like gold, platinum, and uranium. Observing a hypernova from Earth would be a rare, awe-inspiring event. Even at distances of tens of thousands of light years, the explosion would dominate the sky, visible during the night and possibly in daylight. These events also provide crucial insight into the life cycles of the universe's largest stars, showing how extreme rotation, mass, scene, and internal structure affect the final moments of a star's life. Lying quietly, imagine the colossal energy released in a hypernova, the twin jets of gamma radiation, the shock waves rippling across space, and the scattering of heavy elements into the galaxy. The scale, violence, and precision of this cosmic event highlight both the fragility and power inherent in stellar physics. Hypernovae are the ultimate reminder that creation and destruction are intertwined, that the atoms within you may have originated in such a brilliant, violent finale, and that the universe operates on scales and energies far beyond ordinary perception. As you let your imagination drift through this scene, the awe-inspiring spectacle carries your thoughts gently, blending wonder and calm, guiding you into a reflective, restful sleep. A hypernova is not just a massive explosion, it can produce a gamma-ray burst, one of the most energetic events known to the universe. These bursts occur when material from the collapsing core of a hypergiant is ejected in narrow, relativistic jets, moving at significant fractions of the speed of the light. The energy emitted in these beams is concentrated and intense, so that a single gamma-ray burst can release more energy in seconds than the Sun will produce over its entire lifetime. From Earth, we detect these bursts as sudden flashes of gamma radiation, lasting from a few seconds to several minutes, illuminating the cosmos with a signal that travelled billions of light years. The most distant gamma-ray bursts observed originate from galaxies over 10 billion light-years away, meaning we see them as they occurred when the universe was young, less than 4 billion years old. gamma-ray bursts not only demonstrate the extremes of physics, but also reveal the connection between massive stars, their death throes, and the chemical evolution of the universe. The jets can alter nearby gas clouds, compressing them and triggering the formation of new stars, distributing heavy elements forged in the star's core and influencing the early development of galaxies. Imagine drifting silently in space as a gamma-ray burst erupts, a concentrated beam of energy cutting across light years, seeding matter and illuminating the darkness for a brief, extraordinary instant. For a moment, the universe is both terrifyingly powerful and profoundly creative. Lying quietly, envision the brevity and intensity of these bursts, the connection they create across cosmic time, and the role they play in shaping the elemental composition of everything around you. As your mind follows the jet's path across the galaxy, feel the immensity, the brilliance, and the cosmic rhythm, allowing awe to blend with serenity, gently guiding your thoughts towards sleep as you imagine these incredible flashes of energy unfolding silently across the universe. Long before galaxies, planets, or even the first familiar stars existed, the universe endured a vast dark age, filled only with diffuse hydrogen and helium gas. For roughly 100 million years after the Big Bang, the cosmos was completely dark, without a single star to illuminate the void. Then, the first generation of stars ignited, bringing the earliest light into the universe and marking the end of this primordial darkness. And these population 3 stars were unlike anything observed today. Formed from pristine hydrogen and helium, without heavier elements to cool the gas efficiently, they were enormous, reaching masses between 100 and possibly 1,000 times that of our Sun. Their enormous size caused their cores to burn at extreme temperatures, with surface temperatures exceeding 50,000 degrees Fahrenheit, placing them firmly in the blue end of the spectrum. These stars were not only huge but extraordinarily bright, pumping out vast amounts of ultraviolet radiation that ionized the surrounding hydrogen gas, turning the universe transparent and initiating the epoch of reionization. Their nuclear furnaces forged the first heavy elements, carbon, oxygen, silicon, and iron, which were expelled into space through powerful supernovae, seeding the material from which all subsequent stars and planets would form. These explosions were not gentle. The largest of them may have ended as pair-instability supernovae, completely annihilating the star and leaving no remnant behind, dispersing enriched material across thousands of light years. Observing these first stars directly is impossible today, because their light has long since travelled billions of years to reach us, and the stars themselves no longer exist. However, astronomers infer their existence through the chemical signatures found in ancient metal-poor stars in our galaxy's halo. Imagine drifting near one of these early giants, the sky dominated by enormous blue-white spheres, the radiation intense enough to reshape entire regions of space, and the energy from their fusion processes carving path through the primordial gas. These stars, though fleeting in cosmic terms, set the stage for the universe as we know it, creating the first elements essential for planets, water, atmospheres, and eventually life itself. Lying quietly, envision the first light piercing the darkness, illuminating an empty cosmos, and consider that every atom of carbon, oxygen, and iron in your body likely originated in these vanished giants. Let the mind drift across the vastness of early space, feeling the magnitude, energy, and transformative power of the universe's first stars, allowing awe and calm to merge and gently guide you into deep, reflective sleep. While the first stars shaped the early universe, the most massive stars alive today continue to push the limits of size, energy, and instability. Modern hypergiants, though fewer in number, dominate their local environments and teach us about the extremes of stellar evolution. Stars like Westerlund 1-26, R136A1, and VV Cephei illustrate how mass, luminosity, and chemical composition influence stellar life cycles. Westerlund 1-26, located within a dense star cluster only a few light-years across, has a radius exceeding 2,000 times that of our Sun, and if placed at the centre of the solar system, its outer layers would reach beyond Saturn or even Uranus. The cluster itself contains hundreds of massive stars interacting gravitationally, exchanging material and influencing each other's evolution. These hypergiants pulse and shed mass at extraordinary rates, forming enormous shells of gas and dust that radiate in infrared and radio wavelengths. Now, this ongoing material loss enriches the surrounding interstellar medium with carbon, oxygen, silicon, and iron, elements essential for the next generation of stars and planets. Unlike the ancient population 3 stars, these modern hypergiants are subject to additional constraints: metallicity, rotational speed, magnetic fields, and interactions with companion stars. Their outer layers are tenuous and constantly in motion, driven by convection, radiation pressure, and pulsations, producing complex structures in their surrounding nebulae. As they near the end of their lives, these giants explode in supernovae, or in some cases hypernovae, dramatically influencing the chemical and dynamical evolution of their regions. The light from these stars, though often invisible in the optical spectrum due to dust, there reveals their true magnitude through infrared and radio observations, showing the ongoing processes that govern extreme stellar physics. Imagine drifting near Westerlund 126, the crimson surface pulsating, material streaming outward, the cluster illuminated by dozens of other massive stars, each interacting and influencing the other, creating a dynamic, living environment on a galactic scale. These modern hypergiants, though far from the first stars, continue to shape the galaxy, demonstrating that the processes of creation, destruction, and enrichment are ongoing. Lying quietly, imagine the energy, scale, and beauty of these giants, their influence reaching across light years, and let the mind absorb both awe and calm, using the immensity of the universe to gently guide thoughts towards sleep. Even in our modern surveys of the Milky Way and nearby galaxies, many of the larger stars remain hidden from view. Dust, distance, and crowded galactic environments obscure them, meaning our catalogues of hypergiants capture only a fraction of these colossal objects. Some of these hidden giants may exceed the size of known stars like Stevenson 218, lying veiled in dense nebulae or on the galactic outskirts where observations are difficult. NML Cygni and VV Cephei are examples of stars partially obscured by gas and dust, their true luminosity and scale revealed only through infrared and radio imaging. These stars pulse, shed mass, and influence their surroundings, yet much of their activity remains invisible to traditional optical telescopes. Each ejection contributes to the chemical enrichment of the galaxy, scattering elements essential for planets, water, and life. Even without direct observation, astrophysicists can infer the existence of hidden giants through their gravitational effects on nearby stars, subtle luminosity variations, and the structure of surrounding nebulae. Imagine drifting past such a hidden giant, its full magnitude invisible, yet the sheer energy radiating through space, influencing star formation and galactic evolution. These silent giants demonstrate that the universe is far larger and more complex than our senses can perceive, with immense forces operating quietly beyond our view. The outer layers of these stars are tenuous, constantly shedding material, while the dense cores continue fusing elements at incredible pressures and temperatures. Each pulse and mass loss event echoes across light years, shaping the cosmos in ways that will not be fully visible for centuries. As you lie quietly, let your imagination wander to these hidden giants, feeling their presence in the galaxy, sensing the unseen forces, and contemplating the vastness and richness of the universe. Even unseen, they influence everything from the birth of new stars to the elemental makeup of future worlds, reminding us that much of the universe's majesty occurs beyond direct observation. Let the mind dwell on their hidden majesty, absorbing awe and calm, guiding you gently into deep, reflective sleep. Every star we observe is a window into the past. The light reaching Earth tonight from Stevenson 218 began its journey 20,000 years ago, during the dawn of human civilization. Betelgeuse, 640 light-years away, shows us the sky of the late 1300s, while Sirius, only 8.5 light-years distant, reveals light from less than a decade ago. This delay means that the night sky is effectively a time machine. Each star is a snapshot, showing how it appeared when its light first left the surface. For hypergiants and other extreme stars, this concept becomes haunting. Some stars may have already exploded as supernovae or hypernovae, yet we will not witness the event for centuries or millennia. Light travels at the fastest speed in the universe, but across these immense distances, even light takes years, decades, or thousands of years to reach us. The Crab Nebula, remnant of a supernova observed in 1054, illustrates this. The light from the explosion reached Earth in the Middle Ages, yet today we study the expanded remnants hundreds of light-years across. Observing the cosmos in this way connects us to the past, providing insight into stellar evolution, galaxy formation, and the chemical enrichment of the universe. Hypergiants like Stevenson 2-18, VV-Cephei, and R136 A1 may already have completed their life cycles, yet the light we see carries the story of their existence, preserving their brilliance, mass loss, and pulsations across the vastness of space. Imagine lying quietly, realizing that every star overhead is a message from a different epoch, each point of light a time capsule. This cosmic perspective invites awe and contemplation, highlighting the impermanence, scale, and interconnectedness of all things. As you drift towards sleep, allow your mind to travel along the light paths of distant giants, witnessing their history and legacy, feeling both the immense scale and quiet continuity of the universe, and letting the vastness inspire calm and reflective rest. When hypergiants finally reach the end of their lives, the explosions they create leave behind enduring marks on the galaxy, supernova remnants. These remnants are vast clouds of gas and dust, illuminated by the energy of the explosion and the radioactive decay of newly formed elements. They can stretch for hundreds of light years, persisting for tens of thousands of years, providing a visible legacy of stars that once dominated their regions. The Crab Nebula, the Veil Nebula, and the Cygnus Loop are among the most famous remnants, each telling a story of creation and destruction. Within these expanding clouds, heavy elements forged in the cores of hypergiants, carbon, oxygen, silicon, iron, and beyond, are scattered, seeding future generations of stars and planets. Observing a supernova remnant is like reading a cosmic manuscript. The patterns, shapes, and colors record the violent physics of the progenitor star, the geometry of the explosion, and the interaction with surrounding interstellar material. For example, the Hubble Space Telescope has revealed intricate filaments, knots, and arcs of glowing gas surrounding Canis Majoris and other massive stars' remnants, highlighting the turbulent processes that occur when gravity and radiation collide in extreme conditions. Beyond their visual beauty, supernova remnants are fundamental to the chemical evolution of galaxies. Every planet, every ocean, every atom in our bodies can trace its origins to stars that ended their lives in such explosions. The material expelled enriches interstellar clouds with elements heavier than helium, allowing the formation of rocky planets, complex molecules, and eventually life. Imagine drifting through the remnants of a hypergiant's death, vast clouds of glowing gas stretching across unimaginable distances, each filament carrying the signature of a star that no longer exists. The energy and matter released ripple outward, triggering new star formation, compressing nearby gas clouds, and creating the conditions for future generations of celestial objects. As you lie quietly, visualize the intricate, colourful tapestry of supernova remnants across the galaxy, the echoes of violent yet creative forces, and allow the enormity and beauty of these structures to expand your imagination. In this quiet contemplation, the life and death of stars becomes a meditation, guiding your mind toward calm, reflective sleep while connecting you to the ongoing cycle of cosmic creation. From the violent deaths of hypergiants emerge some of the universe's densest and most mysterious objects, neutron stars. When a massive star explodes as a supernova, the core collapses under gravity, compressing matter to incredible densities. A neutron star packs the mass of one or more suns into a sphere only about 12 miles across. A single teaspoon of its material would weigh billions of tons on Earth. Neutron stars often spin rapidly, hundreds of times per second, and possess intense magnetic fields, emitting beams of radiation that sweep across space like cosmic lighthouses. When these beams intersect Earth, we observe pulses, yet a rhythmic pulse of radio waves providing insight into the star's extreme properties. These city-sized remnants are laboratories of physics under conditions impossible to recreate on Earth. The core consists almost entirely of neutrons, forming matter in states that challenge our understanding of quantum mechanics and nuclear physics. Neutron stars can merge with other neutron stars or black holes, producing gravitational waves detectable across the universe and creating kilonovae that forge the heaviest elements such as gold and platinum. Imagine drifting near a neutron star, an incredibly dense sphere, spinning at tremendous speeds, emitting focused radiation and influencing its surroundings with gravity strong enough to bend space-time itself. These remnants are the quiet, enduring echoes of stars that lived fast and died violently, leaving behind objects whose influence extends far beyond their size. As you lie quietly, picture the neutron star's intense gravity, the spinning beams of radiation, and the remnants of its parent star dispersed across space. Reflecting on these cosmic phenomena brings awe and perspective, connecting the life cycle of stars to the very elements that form planets, life, and even your own body. Allow your imagination to embrace this extreme physics while guiding your mind gently into a state of calm, meditative sleep. Some of the largest hypergiants leave behind a fate more extreme than neutron stars, black holes. When a massive star exhausts its fuel, and its core collapses beyond the neutron degeneracy limit, gravity overwhelms all opposing forces, compressing matter into a point of infinite density known as a singularity. surrounded by an event horizon from which not even light can escape. Stellar mass black holes typically contain a few times the mass of the Sun, but hypergiants may form remnants significantly heavier, influencing their surroundings with immense gravitational fields. The event horizon marks the boundary of no return, where anything crossing it, light, gas, or even another star, is inexorably drawn inward. Black holes can exist alone, silently drifting through the galaxy, or in binary systems where they pull matter from companion stars, creating accretion disks that heat up to millions of degrees and emit X-rays detectable across light years. Observing these X-rays allows astronomers to locate and study black holes indirectly, revealing information about mass, spin, and behavior despite their invisibility. Black holes are also engines of cosmic evolution, influencing star formation, galaxy dynamics, and the motion of surrounding stellar populations. Mergers of black holes and neutron stars produce gravitational waves, rippling through space-time, which we can detect using observatories like LIGO and Virgo, giving us insight into the most energetic events in the universe. Imagine drifting near a stellar mass black hole. Space itself warps, light bends, and gravity dominates every motion. The surrounding environment is a swirling maelstrom of gas, radiation, and relativistic effects. For hypergiants that collapse directly into black holes without a visible supernova, the process can be almost silent yet immensely powerful, reshaping the local region of the galaxy and altering the course of surrounding matter. Lying quietly, imagine the invisible pull of these gravitational monsters, their immense density, and their ability to shape cosmic history while remaining unseen. Contemplating black holes evokes both awe and humility, connecting the life and death of stars to the underlying forces of the universe, and reminding us of the extremes of physics that govern reality. Allow your mind to drift through these invisible realms, feeling the immense scale, power, and quiet intensity of black holes, guiding your thoughts gently into a deep reflective sleep. Not all massive stars live and die alone. Many are part of binary or multiple star systems, and under the right conditions these stars can merge, creating objects far more massive than typical single-star evolution allows. Stellar mergers occur when two stars collide or gradually spiral together, combining their mass and angular momentum, often ejecting significant material in the process. The resulting merged star can exceed normal mass limits, forming a hypergiant with unusual properties, enhanced luminosity, and potentially an accelerated evolutionary path towards supernova or hypernova. These mergers can also influence the type of explosion at the end of life, altering chemical composition, internal structure, or rotational dynamics, and sometimes producing highly unusual supernova signatures. A real example is V838 Monocerotis, which underwent a dramatic merger in 2002, briefly becoming one of the most luminous stars in the Milky Way, and leaving behind an expanding, glowing cloud of gas that continues to be studied for its extraordinary properties. Stellar mergers illustrate the chaotic and dynamic nature of star clusters, where interactions between massive stars can lead to extraordinary objects that challenge our understanding of stellar physics. Imagine witnessing two stars spiraling together over millions of years, their outer layers intertwining, generating powerful flows of gas, radiation, and angular momentum, eventually creating a new, colossal hypergiant that pulses with fresh energy. As you lie quietly, picture the turbulent birth of a merged star, the fusion of its cores, the redistribution of energy, and the ongoing mass loss that will shape its surrounding nebula. These events remind us that the universe is not static. It is dynamic, violent, and creative, where collisions and mergers generate objects more extreme than ordinary evolution would permit. Let your imagination wander through the drama and scale of stellar mergers, feeling both awe and calm, allowing the mind to drift peacefully into cosmic-inspired sleep. Some of the universe's most extreme events occur when two neutron stars collide. Unlike typical stellar deaths, these mergers release extraordinary energy and produce phenomena that reshape the surrounding cosmos. Neutron stars, city-sized spheres with masses greater than the Sun, orbit each other in a binary system until gravitational wave emission causes them to spiral inward and collide. The impact generates an event called a kilonova, releasing massive amounts of heavy elements such as gold, platinum, and uranium into space, elements that are otherwise rare in ordinary stellar evolution. These collisions also produce gravitational waves, ripples in the fabric of space-time, that can be detected across millions of light-years, allowing us to observe the most energetic events in real time despite their extreme distances. The energy released in a neutron star merger is staggering. Matter is compressed beyond nuclear densities, temperatures rise to billions of degrees, and radiation floods the surroundings with high-energy photons reshaping nearby gas clouds. Observing such a merger provides a glimpse into processes that create the universe's heaviest elements, forming the raw materials for planets, crusts, and eventually life. Imagine drifting near such a merger, two compact ultra-dense stars spiraling together, colliding with unimaginable force and ejecting material that will seed new stellar systems. The surrounding space is illuminated briefly by the explosion, but the real impact is chemical and structural, leaving a lasting legacy for billions of years. For humanity, these events remind us that even the tiniest particles in our bodies, gold in jewelry, uranium in power plants, iron in blood, trace their origin to the most violent processes in the universe. Lying quietly, let your mind follow the spiraling dance, the collision and the dispersal of elements, feeling both awe and serenity, and allow the knowledge of these cosmic forges to gently guide you into deep, reflective sleep. Even more extreme than two neutron stars colliding is the merger between a black hole and a neutron star. In this rare event, the black hole's immense gravity tears the neutron star apart, swallowing most of its mass while releasing gravitational waves and electromagnetic radiation detectable across vast distances. The collision produces intense energy and can create heavy elements previously forged in the neutron star, ejecting some matter into space to contribute to the galaxy's chemical evolution. These mergers are extreme laboratories of physics, testing our understanding of gravity, nuclear matter and relativistic effects. The gravitational waves ripple across space-time, carrying information about mass, spin, and orbital dynamics, allowing astronomers to probe conditions otherwise impossible to observe. Imagine drifting near such an event. A neutron star spiraling toward a black hole, stretching and tearing under immense tidal forces, matter accelerating to near light speed, and radiation blasting outward in concentrated bursts. This is a dance of destruction and creation on a scale beyond comprehension, where energy, gravity, and matter interact in the most extreme ways. These mergers can also lead to the formation of slightly larger black holes, altering the population of stellar mass black holes in a galaxy, and influencing future dynamics of nearby stars. As you lie quietly, picture the intense gravitational tug-of-war, the violent stretching, and the release of matter and energy into space. Reflect on the extraordinary physics at play, and let your imagination drift gently, absorbing both awe and serenity, preparing your mind for deep cosmic-inspired sleep while contemplating the immense forces shaping the universe. In the early universe, long before stars like our Sun existed, theoretical models suggest the presence of dark matter stars, giant objects powered not by nuclear fusion, but by the annihilation of dark matter particles. These stars, composed primarily of hydrogen and helium, relied on the energy generated by interactions of dark matter in their cores to support their massive envelopes against gravitational collapse. Dark matter stars could have reached sizes millions of times larger than our Sun, far surpassing even the most extreme hypergiants we observe today. Their surfaces were relatively cool, despite the immense mass and size, because their energy source was slow and steady, rather than the intense fusion seen in conventional stars. The potential longevity of these giants is staggering. They may have remained stable for hundreds of millions or even billions of years, far longer than any massive nuclear-burning star. Once their dark matter fuel was exhausted, the stars would collapse, some possibly triggering nuclear fusion briefly, or leaving behind massive black holes that would seed the centers of galaxies. These hypothetical objects illustrate the extraordinary possibilities of stellar formation and evolution in the early cosmos, providing insight into how supermassive black holes could form quickly after the Big Bang. Imagine drifting near a dark matter star. The surface a cool, enormous envelope of glowing hydrogen and helium, stretching across distances that encompass thousands of solar systems, yet emitting a steady, faint light, powered by invisible forces. These giants, though purely theoretical, reveal the range of possibilities that physics allows under the right conditions, expanding our understanding of scale, energy, and structure in the cosmos. Lying quietly, visualize these enormous, slowly breathing giants, their invisible energy shaping the early universe, and allow the immensity and mystery of their presence to inspire awe while gently guiding you into deep reflective sleep. Even with dark matter stars and quasi-stars, there are limits imposed by physics on how large a star can grow. For conventional stars with modern chemical compositions, the Eddington limit caps their mass at roughly 150 solar masses, translating to maximum diameters of around 2,000 to 2,500 times that of the Sun. Beyond this point, radiation pressure overwhelms gravity, blowing away the outer layers faster than the core can hold them, preventing further expansion. In the early universe, stars made of pure hydrogen and helium could grow larger, but even then, structural coherence imposes constraints. A star hundreds of thousands of solar radii across would have light and pressure waves traveling too slowly to maintain stability, behaving more like a diffuse cluster of gas than a coherent star. Beyond these limits, any object attempting to grow larger would either fragment into multiple smaller stars or collapse into a black hole. Hypothetical objects like dark stars push these limits, potentially spanning millions of solar radii, yet the structural coherence that defines a true star would fail at even larger scales. Understanding these limits is essential to grasp why the hypergiants we observe today top out around 2,000 solar radii, and why the first stars, despite forming under different conditions, had constraints dictated by gravity, pressure, and energy transport. Imagine lying quietly and considering these extreme boundaries. Stars larger than Stevenson 2-18 cannot exist without disintegration, and yet the universe finds ways to create objects at the very edge of physics. These constraints, while invisible, define the architecture of galaxies, the evolution of stellar populations, and the potential for matter to assemble into coherent, luminous bodies. Let your mind absorb the scale, the balance, and the physics of these limits, marveling at the precision and power of natural law, while gently drifting towards sleep with a sense of awe and cosmic perspective. Even in the vast surveys of our galaxy and neighbouring galaxies, countless massive stars remain hidden from observation. Dust, gas, and crowded stellar environments obscure these hypergiants, leaving their true scale and luminosity veiled from optical telescopes. Infrared and radio observations reveal some of these giants, like NML Cygni and Vifay, but many others lie entirely unseen, influencing their surroundings quietly yet profoundly. These hidden stars pulse, expand, and shed mass into the interstellar medium, enriching it with carbon, oxygen, iron, and heavier elements, crucial for the next generations of stars and planets. Despite their invisibility, they shape star formation, regulate chemical evolution, and contribute to the dynamics of their local environments. Astronomers infer their existence through gravitational effects on nearby stars, subtle luminosity variations, and the structure of surrounding nebulae, revealing the complexity of galactic architecture and the limitations of human observation. Imagine drifting near such a star, its full size hidden behind clouds of dust, yet the energy it radiates influences vast regions of space, shaping matter and energy across light years. These silent giants remind us that the universe is far larger and more complex than what meets the eye, with immense forces operating beyond direct perception. Lying quietly, visualize the unseen giants, their mass loss and radiation shaping galaxies, seeding new stars and planets, and leaving behind the elements that will eventually form life. The scale, mystery, and quiet influence of these hidden hypergiants expand your imagination, offering awe without disturbance, and guiding the mind into reflective, meditative sleep. The invisible universe teems with activity, and even the stars we cannot see play vital roles in the cosmic cycle, reminding us of the vastness, subtlety, and grandeur of the cosmos as you drift toward rest. At the very limits of what physics allows, the largest stars we know of, like Stevenson 2-18, push our understanding of size, energy, and cosmic evolution. With radii over 2,150 times that of the Sun, and luminosities hundreds of thousands of times greater, these hypergiants dwarf entire solar systems and dominate their local environments. Yet even these giants sit just below the Eddington limit, the boundary where radiation pressure balances gravity, demonstrating that nature enforces a precise upper limit on stellar size. The universe beyond contains countless stars yet unseen, some hidden behind dust or in distant galaxies, and in the early cosmos, hypothetical objects such as quasi-stars and dark stars may have exceeded these limits by orders of magnitude. The scale of these hypothetical giants is staggering. Quasi-stars may have encompassed hundreds of solar systems, and dark stars powered by dark matter annihilation could have stretched across millions of solar radii. The extreme objects, real or theoretical, illuminate the incredible range of stellar possibilities and the profound influence stars exert on the universe. As you lie quietly and imagine these unimaginable giants, consider the energy, matter, and forces they contain, shaping galaxies, creating elements, and driving cosmic evolution. The biggest stars teach us about the delicate balance of forces, gravity, radiation pressure, nuclear fusion that govern existence, and about the fleeting yet monumental impact of stellar lives on the cosmos. Every pulse, every mass ejection, and every explosion contributes to the universe's continuous cycle of creation and transformation. Let your imagination soar across the distances and scales of these giants, absorbing awe, serenity, and wonder. Drift with the understanding that the universe is vast, its stars larger than you can conceive, and that even as you sleep, their light, legacy, and influence continue, shaping everything from the smallest atom to entire galaxies, carrying you gently into a deep, cosmic-inspired sleep. As our journey through the universe's largest and most extraordinary stars comes to a close, take a moment to breathe deeply and reflect on the vastness you've witnessed. From the closest familiar suns to the hidden giants veiled in dust, from the blue hypergiants burning furiously to the slow, majestic red hypergiants, each star tells a story of creation, transformation, and inevitable death. You've travelled across light years in your imagination, seen the first stars ignite the cosmos, and contemplated the unimaginable scale of quasi-stars and dark stars, objects far beyond everyday comprehension. These stars, alive with energy and mystery, remind us that the universe is both immense and intimate. The very elements that form our bodies and our world were forged in their cores and scattered across space by their explosive deaths. As you drift into sleep, let the enormity, beauty, and gentle rhythm of these celestial giants lull you into calm. Feel the quiet pulse of the cosmos, the slow expansion and contraction, the distant light travelling across eons to reach your eyes. When every star you've imagined tonight is a reminder that even in the darkest stretches of space, life, energy, and transformation are always at work. Carry the serenity of this journey with you, letting your mind float among the giants while your body relaxes completely. If this cosmic voyage inspired awe or sparked curiosity, consider sharing it so others may experience the same quiet wonder. Like, subscribe and return whenever you need to drift through the universe, explore its mysteries, and find peace in the grandeur of the stars. Tonight, the universe has whispered its secrets, and as you rest, its giants will continue to shine, unseen yet eternal, guiding your dreams across light years of imagination. Sleep well, traveller of the cosmos, and let the stars watch over you until morning.